Hello and welcome. Here's Mustafa. In this video, I'm going to speak about the calculations involving acids and bases for HL students. Let's start. The objectives for this video are carry out calculations involving Ka, Kb, pKa, pKb, pH, and pOH. Use relationships Kw equal Ka multiplied by Kb and pKa plus pKb equal pKw. First of all, we would like to highlight on some strategic points for the calculations. We have to know that weak acids and bases dissociate partially. For that reason, we could assume that the change in the weak acid concentration is very small and can be negligible because sometimes they will ask you to give an assumption during the calculations. The next point is the dissociation constant is a measure of the extent to which acid or base dissociates. The stronger the acid base, the more it dissociates and the higher the value of its dissociation constant. For that reason, the dissociation constant, which is Ka or Kb, is an indication for the acid or base being strong, or you can use this value for Ka or Kb to compare between acid and bases strength. For a weak acid, we have here the general equation for its dissociation. We have Ha, which is the weak acid. It dissociates to give hydronium ion and its conjugate base, which is A minus. The acid dissociation constant is which is Ka is equal to, of course, is like the equilibrium constant for any equation. So it's the product, the concentration of the products over the concentration of the reactants. But we are not using water here because we are using a diluted solution. So water here is not counted with us in the dissociation constant. For the same with the weak base, we have here the base in water is giving out OH minus and the conjugate acid of the base. We have the base dissociation constant, which is Kb is equal to the concentration of the products over the concentration of the reactants. How to calculate Ka? Calculating Ka for weak acids. First of all, we have to check the problem we have. If you are instructed to use the data booklet, you can calculate Ka directly from the relation which is telling that Ka is equal to 10 to the power negative pKa. Directly from the data booklet, you will find values for Kp, so you can use this formula directly. But if you are not instructed to use the data booklet, or if this acid is not in the data booklet, you have to follow some steps. The first step is to write a balanced equation, which is used for as an indication for the mole ratio. Second step is to calculate the concentration of hydrogen ions or hydronium ions from the given pH using 10 to the power negative pH. In the problem, they will give you the pH, then you have to use pH or the concentration of hydrogen ions is equal to 10 to the power negative pH. Third step is to set up chart for equilibrium, which is initial change equilibrium. Fourth is to find Ka from the formula. Let's check a problem, quick problem. The pH of 0.1 molar H2C2O4 is 1.28. Calculate the Ka for the weak acid. Here we will not use the data booklet because this weak acid is not listed in data booklet, and we are not instructed to use the data booklet, so we can use the steps. First of all, we have to write the balanced equation for the reaction. Here is that H2C2O4. We don't have to forget the reversible arrow to indicate that it is a reversible reaction, so there will be an equilibrium state here. Then we have hydrogen and HC2O4 negative, which is the conjugate base. The second step is, so the first step is to write the balanced equation. The second step is to calculate H positive from pH. pH is here, it's 1.28, so the concentration of hydrogen ions is equal to 10 to the power negative pH, so it's equal to 10 to the power negative 1.28, so the concentration of hydrogens is 0.05248 molar. Then we have to set up the ICE chart, which is very easy. The I, the initial, of course, before starting the reaction, we have the concentration of the weak acid, which is 0.1. We don't have hydrogen. We don't have hydrogen or the conjugate base. The C, which is the change. The change is when the reaction will start. We have to take away some of the concentration of the weak acid because it already dissociates. It's a very small value, but we should subtract this from the initial concentration of the weak acid, which is the H positive, Here is it, the change. So at equilibrium, we subtracted the concentration of hydrogen from the concentration of the initial concentration of the acid. So we have here 0.04752, and here is the concentration of the acid and the concentration of the weak base. Why they are similar? Because as you can observe here, we have, because one molecule of H2C2O4, one molecule here, dissociates to produce one H positive, and one HC2O4 negative. So the concentration of HC2O4 negative at equilibrium is the same as that of H positive. For that reason, they have the same concentration. Then we will apply directly the formula, which is Ka. We have the concentration of hydrogen. Here is that. We have the concentration of the conjugate base. Then we have the concentration of the acid at equilibrium. Then we can use the calculator to find Ka, which is equal to 5.8 multiplied by 10 to the power negative 2. Now, how to calculate Kb for weak bases? Again, if we would like to calculate Kb, we have to return to the relations we have. If we calculated Ka in a previous step, then you can use this formula, which is telling that Kw, which is the dissociation constant of water, is equal to Ka multiplied by Kb, equal to 10 to the power negative 14. So if you are asked to calculate Kb and you already have Ka, so it's very easy. It's just 10 to the power negative 14 over Ka. Otherwise, you should follow the following steps like we did with Ka, but we have to observe the difference. First of all, we should write the balanced equation to give the mole ratio. The second step is to calculate the concentration of OH negative from the given pH. But of course, we have to care that this is not the concentration of hydrogen, this is the concentration of OH negative. So we have to return to this formula or this relation. pKw is equal to pH plus POH. pKw is 14. So if the pH we have is 1, 2, 3, whatever, it's 14 minus pH. Then after calculating the pOH, we can calculate the concentration of OH negative using this formula. The concentration of OH negative is equal to 10 to the power negative pOH. Third step is to set up the chart for equilibrium, which is the ICE, the initial change equilibrium. Find the KB, sorry, it's KB for the formula, from the formula KB equal to the concentration of the products over the reactant. Okay, we have the problem here. The pH of 0.2 molar NaCN is 11.456. Calculate the Kp or Kb for Cn negative. First of all, we have to write the balanced equation. Okay, then we should calculate the OH negative. Why we should calculate the OH negative? Because we need it for this formula. So we have the pH which is equal to 11.456. We will calculate pOH from the pH 14 minus 11.456, which is equal to 2.55. Then we will use the second formula, which is telling that the concentration of OH negative is equal to 10 to the power negative pOH. Then we have here the concentration of OH negative. Then we should set up the chart for the equilibrium, which is the initial concentration of Cn is 0.2 from the problem. Then the change, what is the change? Is the concentration of OH negative formed during the equilibrium. Then we have the equilibrium, which is the initial concentration of Cn negative minus the concentration of OH negative. Again, we assume that because one molecule of NaCN is producing one OH and one HCN, so they have the same concentration. They have the same concentration. Then we apply the expression directly. Kp is equal to HCN, the concentration of HCN, which is here, and the concentration of HCN, the concentration of OH, and the concentration of the base after or during the equilibrium. Then we can calculate the Kb, which is equal to 4.1 multiplied by 10 to the power negative 5. Let's check a past paper problem, which is asking about using the previous formulas. Let's start checking this problem. It's telling you that a 0.12 mole per liter or mole per decimeter cube sodium methanoate solution dissociates completely into its ions. Formulate the equation including state samples for the equilibrium reaction of the hydrolysis of methanoate ions. So we have the methanoate, so we should start by the methanoate ions. What is the methanoate ions? It is HCOO negative. We don't have to forget the state symbol, the state symbols, because you are instructed to include them, plus H2O, which is of course liquid. We don't have to forget the reversible reaction arrow. Then we have OH negative, which is AQ plus COOH Okay, here's it, the equation for the reaction dissociation, the hydrolysis of the methanoate ions. Let's move to the second question. Section 1 and 21 of the data booklet may be used for parts D and 2E. Very good. Calculate the value of Ka, the acid dissociation constant at 298 Kelvin for an aqueous solution of methanoic acid. It's very, very easy because you are instructed to use the data booklet. So we will return to the data booklet here. We have the pKa for methanoic acid, which is 3.75. We already know that Ka is equal to 10 to the power negative pKa. So it's equal to 10 to the power negative 3.75. Using the calculator, you can easily calculate it, which is equal to 1.78 multiplied by 10 to the power negative 10 to the power negative 4. Okay, it's already 10 to the power negative 4. C. Calculate the value of Kb, the base dissociation constant for the conjugate base. We have Ka from the previous point. We have Kb, so it's easy to calculate. We have Ka, so it's easy to calculate Kb because Kw is equal to Ka multiplied by Kb. If we already have Ka, and we already know that Kw is equal to 10 to the power negative 14. So, of course, Kb will equal to Kw, which is 10 to the power negative 14 over the Ka, which is 1.78 multiplied by 10 to the power negative 4. So it will be equal to 5.6 multiplied by 10 to the power negative 11. This is Kd. We still have D and E. Determine the concentration in mole per decimeter cube of hydroxide ion. In the original 0.12 mole per decimeter cube sodium methanoate solution, mentioning one assumption made. Okay, let's return to the original equation we have. It's telling us that we have methanoate. I think it's always preferred to write it again. So we have what we have here is HCOO negative. It dissociates to OH negative plus HCOOH. Okay, we should calculate the concentration of OH, the concentration of OH. What we have here is K. We have already Kb, so we can use we should use Kb. Kb is telling us that Kb. Let's use another. Kb is equal to the concentration of OH negative multiplied by the concentration of HCOOH over the concentration of HCOO negative. Okay, what we already have is Kb. We have Kb from C. What else we have? We should now construct or draw our ICE, initial, change, and equilibrium. Very good. So the initial is 0.1, which is the concentration of the sodium methanoate solution. The change should be the concentration of OH that we wish to calculate, so it will be minus X. So the equilibrium will be 0.12 minus X, and we have OH is X, HCOOH is X because we have the same mole ratio, so they have the same amount. Our assumption here is we can say that the change, do you remember in the second or the third slide, we mentioned that when the weak acid or the weak base dissociate, the change is negligible. For that reason, we can assume that this X is negligible. This X is negligible. So we can say our assumption could be 0.12 minus X is equal to 0.12 because X is negligible. Now we have all the values. We just have to substitute. So we already have Kv from C. Okay, so we will have now Kb will equal to x squared. Why x squared? Because this one is x and this one is x as well, so we have x squared. HCOO negative during the equilibrium is 0.12. So, and of course we have Kv is 5.6 multiplied by 10 to the power negative 11 from here. So now it's very easy to calculate x, which will equal to, I already calculated it using the calculator. So x will equal to the square root of 0.12 multiplied by the value for the Kb. So we, after using the calculator, the concentration of OH negative will be 2.6 multiplied by 10 to the power negative 6 mole meter negative cube. Okay, very good. Now let's move to the next one. It's asking us to calculate the pH. Oh, we already have the concentration of OH ions. So I think it's clear now that if we have the concentration of OH ions, so we can calculate the POH, which is equal to negative log OH negative. You just have to use your mathematical skills. Oh, it's not mathematical skills, your calculation skills using the calculator. So it's negative log 2.6 multiplied by 10 to the power negative 6. Okay, so it will equal to 5.59. Okay, here's the POH. We did not finish yet. The pH, we already know that pH plus POH is equal to 14. So pH will equal to 14 minus 5.59. So pH is 8.41. As you can see, the problem is very easy, but you just have to follow the steps, or to use your to recall the information needed to use Ka, Kb, and know the relations between them. Hope it's clear now, and waiting for your feedback. Thank you.